Hello, everyone, and welcome back to our Earth Science Week programs. It has been a fabulous morning already, and we are now joined by Bridget from ANSTO to look at In Their Element. So, a really great extension if you joined our session this morning from Geoscience Australia, looking at the importance of our elements. So please, if Bridget asks you a question, put your responses in the chat. But if you've got questions at the end for Bridget, put those in the Q&A and we will go through those at the end of our program. Thank you, everyone.
Perfect. Thanks so much, Karen. Hello, everyone. Very excited to see you all. My name is Bridget. I'm from ANSTO. Does anyone, maybe you've heard of the ANSTO before? We're the Australian Nuclear Science and Technology Organisation. We're in Sydney. And today we're going to be talking about elements because that's what we do. We learn and study the world of atoms. So I'm going to share my PowerPoint here and I'm going to find out why I'm talking to you today, because we're a pretty interesting organisation. We do things with atoms, and we've got, weirdly, to do things with very, very tiny, scales at the level of atoms and even smaller. We have huge bits of equipment, and I want to tell you a little bit about those bits of equipment today. So, did you know that we've got Australia's only nuclear reactor? It's here in Sydney. And so this is this bit of equipment up here, the Opal multi-purpose reactor. This is basically where we get atoms and we split them in two. We split them in half. And that particular element is uranium. We use that inside our reactor. We also do really funky things when we split these atoms of uranium apart. Maybe you've learned about protons, neutrons, and electrons, perhaps. When we split these atoms apart, some of these neutrons come out and we can actually use these for research in this section. We've got thousands of scientists every year that come and use that. And with our reactor, lots of people think that we make power and electricity, when in fact we don't. We instead make nuclear medicines. So people who might need a special medical scan or maybe have a particular disease that they need treated, something like cancer perhaps, we can help and we make particular medicines that can help with that. And who's heard of carbon dating? I'm sure lots of you have heard of carbon dating before. Well, we have special equipment here called particle accelerators that can do that type of work, that type of carbon dating and even more. So that's what's happening in our Centre for Accelerator Science. And I wonder, is anyone here from Melbourne today? Quick shout out on the chat. If you're here from Melbourne, let me know. So we actually have a facility down in Melbourne and it's called the Australian Synchrotron. And this is a big facility that accelerates another tiny particle called electrons, and they get them almost up to the speed of light. And we do lots and lots of research with that. We've got people from New South Wales and South Australia, no one admitting to coming from Melbourne yet. That's okay, it's a safe space.
We had someone in the Q&A say that they're from Melbourne.
Oh, very good. All right. So that's why I'm talking to you today, because we do lots and lots of research about atoms. But what is an atom? So I've got a circle up on the screen here. And you can see by the scale bar down the bottom, that circle is very, very small, 0.1 nm. Remember, the N is nanometers. So this is 1/10 billionth of a meter wide. And this is the outside of an atom. This is the electron cloud. But remember, the inside of the atom is even smaller. So the inside of an atom, remember, is the nucleus, and that's 1/10,000th the width of this bigger circle. So we're talking about tiny, tiny objects here. Now I want you to, whenever I say these sort of numbers, they don't really mean much to me. I need to sort of visualize it. And so one way I visualize it is if I pluck a hair from my head out, and I was to look at this hair really close, and I've got a picture of this over on the left. This is using one of our electron microscopes. And this is the width of a human hair. Does anyone want to guess how many atoms you could fit in a line across the width of that hair? Or if you're really good at maths, you can actually figure it out using the numbers and the scale bars I've given. Who wants to guess? Pop it in the chat if you know. How many atoms could fit in a line across the width of that hair? Very good. So we've got 3 correct guesses. You're right. We've got 1 million atoms that can fit across the width of that hair. Just shows you how tiny these little atoms are. Now, another way to think about an atom, because again, they're very small, they're sort of hard to visualize. Imagine you had an atom and you blew it up to the size of a core stadium. You know, the big, football stadium at Sydney Olympic Park. So if you got an atom and blew it up this big, so the big netted structure is where the electron cloud would be. Who could guess what is an object that would be about the same size as the nucleus? Remember, the nucleus is pretty small. What's an object that might be about a similar size? Ooh, good guess, a soccer ball. It's actually a little bit smaller than that. What's another object that might represent just how small that nucleus is? Yeah, we're getting closer now. A golf ball, I reckon it's about the size of a grape. So that just shows you that the space inside an atom is mostly empty space. So you've got all of this mass inside the nucleus, which is very tiny, and then the electrons are all the way on the outside, and the rest of it is empty space. So if your teachers ever accuse you of having nothing between your ears, you can say, yes, that's right, miss, or that's right, sir, because you are made up mostly of empty space. Now, if you have studied atoms in class, you've probably come across a diagram like this before, I'm sure. So remember, you've got the nucleus in the middle and little positive protons in the inside. And then these blue circles, who can tell me what they are? What are the blue circles on the inside of that nucleus? We've got the positive protons. What are the blue ones? Does anyone know? Has anyone looked at that one yet? Pop it into the chat. Very good. They are neutrons. Well done. We've got neutrons in the middle, and then around the outside, we've got our negative electrons. Okay. Now, just to emphasize to you that we really have the majority of all of the mass inside the nucleus. So now this is a bit of a complicated table. I'm going to show you the important part. So you can see over on the left says protons, neutrons, and electrons. And then it has a part that says approximate relative mass. Now, protons and neutrons are pretty heavy when it comes to atoms. They've both got a mass of 1. But look how tiny the mass of the electron is compared to the proton and the neutron. They don't weigh anything. So really, the mass of that atom just comes from what's inside the nucleus, the protons and the neutrons. Now, you might have seen the periodic table before. And if you haven't, we're definitely going to be looking at it in more detail today. Remember, the periodic table is made up of a whole lot of different types of atoms, and they are elements. And remember, on the periodic table, each element has a square of its own. And it's got a couple bits of information on that square. And in fact, if we go back, you can see inside this atom, if you were to count up the number of protons, let's count them now. 1, 2, 3, 4, 5, 6, 7, 8, 9 positive protons of those red circles in the middle. So we would represent this on our periodic table, something like this, but there's some information missing because I want to find out from you what you already know. So you can see we've written the number of protons at the top as a number 9. This is also called, does anyone know what this is called? It's called the atomic something. The number of protons is called the atomic, oh, Charlie, you're so close. Not the atomic weight. Starts with N, atomic something. It is the atomic number. That's right. So remember, the atomic number is the number of protons inside the nucleus. Very good. Now, Charlie, I'll get you to answer this question, or you've already answered it really. This number down the bottom, this 19, is the atomic weight. It's the number of protons and neutrons all together. Okay. Now, who knows their periodic table? Who knows which element has 9 protons? Who can pop it in the chat? Which element are we talking about here? Which mystery element haven't we named yet that has 9 protons? What is it? Ollie, yes, you've got it. It is fluoride or fluorine. So fluorine has a particular symbol as well. So fluorine, we give a special symbol because we can't be bothered writing it out all of the time. And when scientists write it in their special equations, they don't want to have to write out the whole thing. How do we represent fluorine as a symbol, as a 1 or 2 letter symbol? What is it? What's the symbol for fluorine? Pop it in the chat. Close. Yes, Tennille's got it. It is F. That's right. Well done, Melinda, too. So this is called the universal element symbol. All right. So now we're going to learn more about the periodic table. And to do this, I want to take you back. I want to take you back to about 3, 4, 5,000 years ago when we had no idea about the periodic table, but we did know about some elements. So I'm going to change, just bear with me. And we're going to look at a couple of different elements here. Now, the first one I want to introduce you to is this. This is gold. And this is one of the very first metal elements to be discovered by humans. And you might think about how you find gold. So, you know, in the gold rush days, they might have found it in rivers and might have found it, if you're really lucky, as a nugget. And so this is one of the first ones discovered because it can be found as a pure substance, not necessarily combined with other things. Often you find it just as a lump of gold, okay? And, you know, this is used many, many thousands of years ago. So you can use it to make jewelry and ornaments and tools. Another one that they found at about that time was copper. Okay, so you can see that's another shiny metal. So these are both metals. They're both what's called malleable, so that you can beat them with a hammer and change their shape. And they're very shiny, so they're very pretty. And because they were fairly rare, the items that got made from these ended up being very prized possessions. So all the way back in Egyptian times, the ancient Egypts excelled in making gold, and it was found in all sorts of things in their life. So the old pharaoh tombs had lots and lots of gold in there. In fact, the whole sarcophagus, or the innermost coffin of Tutankhamun, very, very well-known pharaoh, was made entirely of gold. It was 110 kilograms of gold. Okay. And with copper, we know that we've found copper beads that are more than 10,000 years old, okay, in northern Iraq. So we know that they've been used for a very, very long time. And they could find that they could extract copper when it wasn't found as a lump. They could extract it by putting it into a fire, and they could extract it in that way. Okay, so we'll put our gold and copper to the side. The next one that I want to introduce, which is again a very well-known older element, or at least one that's been known for a long time, I'll see if I can get that focused, is lead. Now, this is one of the very first metals, again, known to humans. It's very easy to extract because you can do it from inside a fire as well. And the ancient Romans used to use lead inside their metal pipes. So until they started to find out that it started to make people a little bit crazy because it got into the water, it wasn't very good for people's health. In fact, they used to put it in people's bowls. They used to put it in makeup until fairly relatively recently, actually, too. It was used in paints and in petrol. But because we know the health effects of lead now, they've started to take that out. It is very heavy metal. So maybe if you go fishing, maybe you use sinkers that are made out of lead. At ANSTO, we use lead because it's a very good shield of radiation. So when we make our medicines and ship it out to hospitals, we put lead around it to stop the radiation coming out. Now, the next one. This is sulfur. I'll get that to... There we go. This is sulfur. So in very ancient times, they called it brimstone, which is very dramatic. And you can see it's commonly found in that yellow form. So around volcanoes and things like that, you might say that sort of yellowy powder. So it's very distinctive. And it also has a very distinctive smell. So when it's combined with hydrogen, you get hydrogen sulfide gas, and that's rotten egg gas. So everyone's probably smelt or heard of that smell. It was used a long time ago by the ancient Greeks because they used it as a preservative. So they used it to preserve their wine. So I want to ask you, compared to the other ones that we looked at, so we had gold and copper and lead. This one in the middle here, sulfur, is that a metal or a non-metal? What do you think and why? Is sulfur a metal or a non-metal? Yeah, that's right, Rebecca. It is a non-metal because you can see all of these other ones here. They have a shiny luster and you can bend them and you can hammer them into different shapes. Sulfur is almost like a powder. So if you had a big block of sulfur, if you hit it with a hammer, it would just break everywhere. It would sort of crumble. Okay. And then we also had someone say that lead is from pens. Now you can see the pencil I'm using here. This is like what you'd call a lead pencil, but the grey part inside that pencil is actually not lead. It is carbon. Okay. But it's known as a lead pencil because very, very early on, they did used to use lead inside those pencils, but now they use carbon. Now, why do you think these were some of the first elements to be discovered? Well, it's because they were found naturally. So you might find some of these naturally in the environment, like sulfur or gold, or if you put some rocks into the fire, you might accidentally get copper or lead. So they were very easy to extract. Okay, let's have a look at some other ones. The other one too, did you notice? You see the letters on each of these. So this is gold. It's got the symbol AU. I would have thought it was GO for gold. What about copper? Should be CO, right? Why is it CU? And PB, it's not LE for lead. Does anyone know why have we got these weird symbols for these elements? Yes, REN, Zami, it is Latin. That's right. So when they were discovered a long time ago, people weren't speaking English, they were speaking Latin. So these are, because of the Latin names of these, this is for gold, the Latin name is aurum. For copper, the Latin name is cuprum. And for lead, the Latin name is plumbum or plumbum. Okay. All right. Let's check this out. I'm going to talk about the next one, which was found in ancient times, which was tin. Okay, another crazy symbol there. It's not TI, it's SN. because its Latin name was stannum. It had a really important part in human history because when they mixed copper with tin, they made a mixture of metals, an alloy called bronze. And you might have heard of the Bronze Age. Okay, so this was able to make harder tools and harder weapons. And if you imagine you go to war with a neighboring tribe and you have swords which are harder and stronger than theirs, then you're likely going to win. So this is a big advantage. Now, another one that they found a long time ago is this one. What does Fe stand for? Pop it in the chat. What's Fe? What element is that? That's right, it is iron. So the Latin word for that is ferrum. And again, it's been known for a long time because originally they found it in meteorites. So they did know that it could be as its own element. Usually they find it as an ore. So again, they had to put it in the fire. But interestingly, they had to work a bit harder to get this out of an ore in the fire because they had to get the fire really, really hot. So what they would do is they'd put some extra charcoal, extra carbon in the fire and blow some extra air into the fire and get it really, really hot. And this is how they were able to extract iron, okay? And so this was the start of the Iron Age. Again, they were able to make stronger tools and stronger weapons. Okay, now, let's swap this over because I want to show you something that is interesting. These aren't just stories that I've told you. There's a reason why I've talked about this. So when we've got gold, remember, it was found naturally as a metal, and sometimes copper is as well. But most of the time, copper and lead, in order to extract those, we needed to roast them in the fire. And iron, we had to roast that one in the fire too, but at an extra high temperature. So we need to put carbon in there. Now you see that over on this side, and hopefully you can see this, these ones are the least reactive because they tend not to react with other elements. So they often are found naturally by themselves. They like to hang out by themselves and you can find them as a lump. But those ones which are more reactive over here, you have to work harder to get them by themselves, to get them to be a pure element, okay? Now, remember that idea of reactivity, because we're going to talk about that a little bit later on as well. Okay. What have we got next? Now, I want to stop the share for a minute because scientists kept working to try and figure out how many different elements there were. So, thousands of years ago, they'd found the common ones. But then they really started to focus on trying to find all of the different elements that they could. So they started not just roasting in the fire, but doing lots of other cool chemistry to see if they could get and find other elements. So after about 8,000 years, they only knew 15 different elements. So they need to try something different. So they might add acids, or they might heat them again and then add something else to them and separate them and see what they could find. So from about 1750 through to 1800, they doubled the number of elements that they knew. So they found another 18 different elements. They really worked hard, and that took them to a total of 33. I want to show you one really important element. Now, I don't have a little circle of this element, but I'm going to show you this. Now, this is an interesting container. This container contains an element called molybdenum. Now, molybdenum was discovered all the way back in 1778 by a Swedish chemist. And he found it in a particular mineral, and he had to work pretty hard to get molybdenum out of this mineral. So he added some acid, and then he ground it together in some oil, and then he heated it up, and eventually he made this metal. Now, the metal molybdenum, and you can see on the periodic table behind me, let's see if I can find molybdenum up here. MO. There we go. That's molybdenum. And we use it at ANSTO because it's really a very important precursor for a special medicine that we make. So this medicine is used for all sorts of diagnostic scans. And you can see we make a radioactive form of this medicine. And we have to send it out to hospitals in a very special container like this, very heavy. Now, this is a whole lot of shielding. Remember, we've got shielding. What was the element that we used for shielding before? We talked about it being really heavy. That's right, we use lead for shielding. So we've got lead in here. And inside this little vial, we've got some molybdenum. That's a very, very important precursor for a medicine for us. Discovered more than, almost 300 years ago now. Okay, so again, scientists kept working hard to find more and more elements. So they had to become more creative about how they started to separate them. So, another 50 years going on, they had discovered another 25 elements. And so by about the middle of the 1800s, in total, they had 58 known elements. And one of the really important ones they found at this time was silicon. Now, this is a big block of silicon, okay? So this is one of the, I think it's the second most abundant element on Earth. But how come they hadn't discovered it until, nearly 200 years ago? Well, it's normally found as sand. So it's usually combined with oxygen. So they need to figure out how to separate it. And what they did was they used electricity to separate it. So that's why, because they didn't really have a good handle of electricity until fairly recently, it took them a long time to be able to use electricity to separate this and make it pure silicon. Now, looking at this, you can see that it is shiny. But can you also see there's little chips, little bumps and cracks in here? And this is because silicon is not a metal. And it's not a non-metal either. It's something weird called a semi-metal. So it's got properties of a metal because it's nice and shiny. But if I were to drop it, it would smash, okay, like glass. So it's very brittle, like a non-metal. This is really important for us at ANSTO because we receive this from overseas. We put it in our reactor and we change it into a semiconductor for electronics. Okay, so it can be used in all sorts of electronics, especially things like renewable energy circuits. And so it can be used to conduct electricity. All right. So I'm going to pop up this again. And I want to reintroduce you to the periodic table now because we've done some pretty cool stuff looking at interesting elements that have been discovered over the ages, what they're used for, how they were discovered, how they're used at ANSTO. Did you know that on the periodic table, we've got 118 elements in total? You see the last one there, oganesson, 118. There's probably going to be more that are discovered over time. But there are really cool properties of the periodic table. Like if you look at this and look at the shape of this periodic table, you go, it's a pretty funky shape. Why don't they just put it in a big rectangle? Why are these sort of like extra bits hanging off here? Well, there is actually a rhyme to that reason. Because you can see each of these squares shows you can see up for hydrogen here, I've got a little circle around the number there. It's the number of protons. So the atomic number. And then you can also see that they are labeled in rows. So I've highlighted the first row here. It's only got 2 elements. But that shows you a little bit about the electrons in those elements. So if you haven't learnt this yet, you might start learning this in year 9 and year 10, that electrons occur as shells. So in the first shell, you can get 2 electrons. In the second shell, you can get 1, 2, let's count how many elements are in this in the second row. 1, 2, 3, 4, 5, 6, 7, 8. You can get 8 electrons in that second shell. And same as in the third shell. So that's the reason why we've got this funky shape for the periodic table. There's also columns in the periodic table. So elements that are in the same column tend to have similar properties as well. So you can see this column that I've highlighted over here. These ones are all gases. And they also have a full outer shell for their electrons. Or this column over here, these are all very reactive, okay? So these are the alkaline earth metals. So things that are in the same row have similar properties. So you'll learn more about that when you get to that subject in class. But I want to show you a couple of other interesting patterns here, and I'm going to pick this row. So you can see in this row, starting with sodium. As you go from left to right along this row, you can see at the start, we've got a metal. This is sodium, it's a metal. And as we go from left to right, we end up getting, we go metal, sodium, metal, magnesium, metal, aluminium, and then we get to silicon. Remember, silicon was a semi-metal. Now, as we go further along this row, then we've got phosphorus, sulfur, chlorine, argon. They are all non-metals. So a really interesting trend across this row and across the periodic table in total is that things go from left to right, become less metallic. Okay. Another example is if you have a look at a column. So if you have a look at this column, we start at the top with nitrogen, and that is a non-metal. So is phosphorus. And then we get down to arsenic and antimony. They are both semi-metals. And then further down the row, we get to the metals, bismuth and moscovium. That's a cool word, moscovium. So you can see a similar trend here down the row. So it becomes more metallic as you go down the row. So I just wanted to introduce you to that. That's not something you need to remember, but it's really something to be aware of, that when you start learning about the periodic table in class or at home, that there are these really interesting patterns in the periodic table, and there's a reason why it's been set up that way. Now, to finish off, I want to do a little bit of a quiz with you. Now, I wonder how many people have a copy of the periodic table with them at home. If you have a copy of the periodic table in front of you or nearby you, can you pop that in the chat, please? So I just want to get an idea of how many people might be able to play along. Who's got one? Chloe's got one. Melinda, yes. April, Zoe, yeah, Rebecca. Okay, we've got a few people who've got a periodic table. Might do something fun to finish off. I have a bit of a who am I game. And what I'm going to do is I'm going to give you some clues. And I want you to see if you can pop into the chat what your guess is for the element that I'm pretending to be. Okay, so the earlier you guess and get it right, that person will win. Okay, so which one should I start with? I might start with, okay, I've got the one that I'm going to start with. You ready? Okay, who am I? Remember, write into the chat once you think you got the answer, and you can guess a couple of times, I don't mind. Who am I? I am a non-metal element. Hint 2. I am a black solid element. No, not sodium, not argon, not iron. Iron. Hint 3. I am used by your thyroid gland in your throat to make thyroid hormones. That's a big clue. So remember, I'm a non-metal. Lots of people giving me metals here. I need a non-metal. I'm a black solid metal. I'm used by my thyroid gland to make thyroid hormones. No one's got it yet. When I'm heated, I sublime to make a purple vapor. Now, hang on. Josie. You just got in before Lottie. The answer is iodine. Very good. So Josie and Lottie, I'll give that one to you both. Well done. Because the last hint I was going to say is I belong to the halogen group. Okay, so remember the halogen group is up here. So starting with fluorine, this group, this column here are the halogens. Okay. All right, very good. You ready for another one? Let's see if I can find a different one. Ooh, this is an interesting one. Okay. Who am I? I was once worth more than gold and silver. Hint 2. I am the third most common element in the Earth's crust after oxygen and silicon. Now, we have a very early winner. Marnie, how did you get that so quickly? Very good. I'll give you the other hints for that as well. Australia is the world's largest producer of my main ore. Well done, Marnie students. I am used extensively in aircraft construction because it's very light, right? You don't want to make an airplane out of something really heavy. You need something light like aluminium. Remember, aluminium is used in soft drink cans. And the other hint was I am in group 3 of the periodic table. So group 3, 1, 2, 3. This one here, starting with boron, aluminium, this column here is group 3. Okay, very good, guys. Ooh, I reckon we've got time for 1 or 2 more. Okay, let's try again. Who am I? I am a gas. I am found in tiny amounts of air. Everyone's gone really quiet. Any guesses? I'm a gas and I'm found in tiny amounts of air, not nitrogen, because nitrogen is like about 78% of the air that we breathe. My group were latecomers to the periodic table. I am the 5th most abundant element in the universe. I'm just checking to make sure no one's got it yet. No, no one's got it yet. And I am used for advertising. All right, we've got an answer. Lottie. Neon. Now, you've all heard of neon signs, right? You know, there's bright neon signs that sort of, you know, say open or something like that on a shop. That's neon gas. So remember, neon is one of the noble gases, and it's in this group all the way over here, okay? So it's all the way up the top here as neon. Okay, I think I've got time for one more.
Just wanted to let you know that Millie and Tennille also got it in the Q&A.
Ah, very good. Sorry, I'm not monitoring Q&A, so thank you, Karen. Thanks for that. Yeah, pop your answers into the chat, guys, because I can probably only monitor one stream of things at once. All right. Last one. Which one should I put? Ooh, can I give you a tricky one? Because you guys are pretty clever. This one is tricky. Okay. Who am I? I am a transition metal found in the middle block of elements on the periodic table. Now, what does that mean? So the transition block, you see on this periodic table behind me, the transition block is this part in the middle. Okay, so it's somewhere in here. I don't exist in nature. So I'm not found naturally in nature. I wasn't discovered until 1937. No, no one's got it yet. Ooh, Ollie, you did get it. I wonder if you guessed it. I wonder if you knew, because technetium is the right answer. The other hints that I was going to give is that Mendeleev predicted my properties nearly 60 years before I was discovered. And one of my isotopes is one of the most important radioisotopes used in nuclear medicine. We make it here at ANSTO. So remember, this was the one I was telling you before, has molybdenum in it that actually turns into technetium. And that's what we use inside people for their scans. Very good, guys. Now, does anyone have some questions? I will open the Q&A now. And happy to answer any questions if we've got hopefully still 5 minutes left. Karen, you guide me on
Yes.
time.
We do have some questions. So Jody was asking, is the rarest element astatine? Now, I don't think I pronounced that right, but
I don't know either. And I don't know whether it is the rarest element either, Jody. I'm going to have to send you to Dr. Google.
I did Google and it does say it is extremely rare.
There you go. I think it's pretty hard to say that one particular element is the rarest. There's a whole lot of rare earth metals as well. So it's pretty hard to say which one is the most rare. But yes, it certainly sounds like it's very rare.
So some questions about some of the gases. So Lisa was asking, how did they find helium? Because it's a gas. How did they discover that?
I don't know off the top of my head, but yes, it is naturally occurring. And did you know also that there is a bit of a shortage of helium at the moment? So you know that, sometimes you can buy helium balloons, or you can buy a tank of helium to fill up your balloons. There isn't like it's a limited resource. So I don't know exactly how they found it, but it's something that we need to preserve at the moment. So it's become very expensive, and they want to make sure that we use it properly.
Yeah, good point. So Ari and Zemi were wondering, how many more elements do scientists think there still are that they haven't found?
That's a good question. Well, so on the periodic table, we don't have gaps. So, when they first made the periodic table, Mendeleev put together the periodic table, he put gaps in because he thought that there were elements that they hadn't discovered yet, and they have discovered all of those gaps. The ones that they're now discovering, because they're actually artificially making them, are on the end of the periodic table. So you know that we've got 118 elements. The ones that they will discover from now on might be 119, number 120, number 121, because they actually make them in particle accelerators. They don't last very long. They might last like less than a second before they change into something else. So who knows? Who knows how many are left?
Wow. Well, that links to how many are there still undiscovered. So we just don't know the answer to that one. So there was a few questions around that. Chloe was wondering where and how zinc is found.
Well, it is a metal. And I think from what I remember, again, I would have to consult Dr. Google, but I think zinc is one of those ones that they had to extract via electrolysis. So they didn't find it until sort of later because they needed electricity to separate it.
Excellent. Now, do you have a favorite metal?
Favorite metal. I think off the top of my head, probably copper. I think it's a pretty funky color because it's like a really cool, yeah, there you go. So you can see on Karen's bracelet there, on the inside, it's sort of like a reddish brown, but on the outside, it turns this really cool green when it oxidizes. So I think that's really cool.
I wore it especially because I was thinking about elements today. So Eloise is wondering which element was the most recently discovered?
Yes, there are 4 which have been recently discovered. They are these ones. I don't know if you can see them. They were recently discovered and only recently named in 2016. So I think they were, I'm going to get this wrong. They're one of these ones. So there are 4 along here in between number 113 and 118. Okay, that were very recently named. Okay, so they were quite recently produced in an accelerator, and they officially got their names, 9 years ago.
Wow, that is recent. So we've got one last question we'll have time for.
Mm.
What does rare earth actually mean?
It does mean that they are rare, and it does mean that, let me see, we've got rare earth metals, I'm trying to find one that is a good example. Things like, got ytterbium and erbium and things down here. So you can see this bottom part of the periodic table, okay, especially in these lanthanides section here. We've got a few rare earth metals here. Basically, exactly why they're called rare earth metals, I would have to do a bit of digging as well, but they're really, really important for a lot of our technologies. So in all of your mobile phones and in all of your computer chips, there are very small amounts of rare earth metals. And so that's why mining companies and various countries are really interested in making sure they have a good supply of rare earth metals. And again, they're limited. So that's why we either need to find our own, or we need to have a really good collaboration with other countries that have them. So that's why those international ties are really important.
Excellent. Well, thank you so much for sharing all of that amazing information, Bridget, and really great to hear more about what ANSTO does and really the importance of the work there to, keep us all healthy as well, all those medical isotopes and all sorts of amazing things. And thank you everyone for joining with your incredible questions. And I liked how many people had the periodic table right near them. I found my old little pocket chemistry high school book, and it's a bit of a dictionary, and it had my little periodic table in there as well. So I also had one quite nearby.
Don't go anywhere without it.
Well, it does come in very, very handy. So I'll be sharing this information and links to ANSTO and the recording of the session shortly as well. So thank you so much for joining us. If you want to continue to test your knowledge, at 1 o'clock we have our lunchtime trivia if you'd like to join us for that session as well. So I look forward to seeing you all again soon, and a big thank you to Bridget from ANSTO for sharing that amazing information.
Thanks again, Karen. Thanks, guys.
Bye, everyone.
Bye.
This session for Earth Science Week is proudly sponsored by Geoscience Australia and brought to you by Virtual Excursions Australia.